so let me draw this behemoth of a circuit that I have asked you to analyze. If I'm not mistaken, we have something like Vn, sorry, is being fed into R sig in series with Cn. We have a resistance R1 here, a resistance R2 here, a resistance RE here, a capacitance CE here, this is RC, here is C out, here we have our load resistance RL, our output pin V out, and these are both at VCC. So let's start with this. Did I draw it correct? Oh, it's a BJT, not a MOSFET. Okay, sorry. Other than that, did I draw it correctly? Big difference, yes, as you guys found out. All right, so let me talk you through the way that I approach this problem, which hopefully and fundamentally makes some sense here, okay? So the first thing that I did is I effectively just established a bunch of different node points at which I'm going to develop transfer functions. So I'm going to call my base node Vx. I'm going to call my collector node Vy. And I'm going to call this guy VZ or V out, either way, because they represent the same thing. Okay. And my goal here is effectively to say that my transfer function H low of S sorry. I feel like I have one more transfer function using the Thevenin equivalent voltage. Yeah, I will. Okay. So we'll get to that in a second. So I'm going to have Vx over Vn multiplied by Vy over Vx multiplied by Vz or V out over Vy to get the relationship between the output and the input. And then I went one step further and I treated everything to the left of this guy as a Thevenin equivalent, which I'll do in a second to make figuring out what's going on ostensibly a little bit easier. So effectively, I'm splitting this transfer function into Vthev over Vn times Vx over Vthev to make the math mildly more digestible. Okay. All right, so let's start with what I hope is an obvious question. Does that methodology make sense? Because that allows us to effectively look at this circuit in easily digestible bits, most of which should at least be vaguely familiar, okay? So let's start with the Vthev over Vn portion. Okay. All I'm doing is replacing everything to to the left of the red dashed line with its Thevenin equivalent. So how would I get my Thevenin equivalent voltage by inspection here? Exactly right. It's a simple voltage divider circuit. So we're going to have VThev is equal to Vin. Well, VThev is going to be the voltage present here at this node. So it's the voltage drop over R1 in parallel with R2. So I'm going to treat that as R1 in parallel with R2 over R sig plus 1 over SCN plus R1 in parallel with R2. And with a trivial amount of manipulation, I can then find that VThev over Vn. Let me make sure where I have this written down very specifically. Looks like I don't have it written down here. It's written down on my board upstairs. That'll be okay. We'll solve it out real quick.
Slightly wrong too.
Okay, perhaps.
It's missing a C in on top.
That should be SCN R.
SCN R1 in parallel with R2 over 1 plus, yeah. So SCN R1 in parallel with R2, because we're multiplying through by SCN over SCN. And when I multiply 1 over SCN times SCN, I get 1. And then I'm going to have SCN R sig plus R1 in parallel with R2. That should be legit. I'm very surprised that's not what's written on my board, because that is absolutely what's written in on my math cat thing. All right, while we're at it, we need to get the Thevenin equivalent impedance. So what's that going to be? So from that, we're taking the red line, we're looking in this way with the input voltage shorted out, right? So R1 in parallel with R2 in parallel with this impedance, right? So ZThev is R1 in parallel with R2 in parallel with R sig plus 1 over SCN. And so I'm just going to do some manipulation on this while we're here. So to me, that looks like R1 in parallel with R2. I'm just treating that as a single resistance to make my life a little bit easier. Times R sig plus 1 over SCN divided by R1 in parallel with R2 plus R sig plus 1 over SCN. And so now I'm going to multiply by SCN to clear some things out, right? So if I multiply by SCN in the numerator, that's going to leave me with R1 in parallel with R2 times 1 plus SCN R sig. And in my denominator, that's going to leave me with 1 plus SCN R sig plus R1 in parallel with R2, if my algebra here is correct, and I believe it to be so. So anybody have beef with VThev or ZThev? Okay. All right, so what I'm going to do now is I'm going to redraw my circuit. So I have my input voltage Vn connected, excuse me, my input voltage V Thevenin connected to my impedance Z Thevenin. There's the base of my BJT connected to my emitter. I'm going to have an impedance ZE, which is simply RE in parallel with 1 over SCE. Up here, I'm going to have RC. And then here I have C out, RL, and V out. And here's my node Vx, Vy, and again, Vz. All right, so now I want to talk to you guys about how I looked at this thing. Okay? So I looked at this as a common emitter amplifier that has a base impedance ZFEV, emitter degeneration from this guy here, ZE, and then I can see that VY, so my output node is this guy over here, but for a standard emitter degenerated common emitter amplifier, I'm going to lump all of this into a single impedance that I'm going to call ZC. Okay. So this is where I'm going to get those transfer functions, most of the transfer functions that I originally talked about. So let's set things up for them right now. The first one is going to be Vx over Vthev, and we're going to come back to that in a bit because that's the longest and biggest ugly looking expansion that we have to do. So let's save the best for last, as it were. Okay. So in 335, we analyzed this circuit, except it only contained resistance, right? How we analyzed it was we treated it as the transfer function between Vx and Vy, where we were just taking our output at node Y, multiplied by the transfer function between Vx and Vthev. Okay, we're going to do the exact same thing. That treatment effectively says that we have Vx over Vthev as a voltage divider circuit, where we want the resistance looking in through the base divided by Zthev over, divided by Zthev plus the resistance looking in through the base, right? So for a degenerated common emitter amplifier, if we're looking in through the base, what we see is R pi plus beta plus 1 ZE. So if we look in here, I'm just going to call this Zn prime. This is R pi plus beta plus 1 ZE. And from this, Vx over Vthev is simply, and it is not particularly simple once we expand it, as you guys who've come to my office have seen, R pi plus beta plus 1 ZE over Z thev plus R pi plus beta plus 1 ZE. And so we'll wind up having to expand this portion out to see what poles and zeros are associated with that part of the transfer function. Now let's talk about what we see looking between X and Y. We have a degenerated common emitter amplifier, right? So Vy over Vx is just going to be negative GM ZC, because we have an impedance attached to node C now, over 1 plus GM ZE, where we're treating everything attached to our collector node, or everything attached up here from node Y, as an impedance ZC, where that would just be RC in parallel with RL plus 1 over SCL. We'll treat that in a little bit. And then lastly, we have a transfer function for this voltage divider connected at the output, right? Which is going to be V out over Vy, which is going to look like RL over RL plus 1 over SCL. We're going to work our way from the output back towards the input, because that's the least complicated towards the most complicated. Okay. But before we do that, does anything seem wrong with this methodology? So just breaking the circuit down into digestible bits that we arguably know how they work. All right, so our transfer function for V out over Vy is pretty dang strict. Yes.
Your typical analysis, how large do they get? Like how many parts do you have to break down?
So for an integrated circuit, I deal strictly in MOSFET, so that makes things much, much easier. Because we don't have to deal with that R pi coupling our base to our emitter at all. But beyond that, it's literally the exact same thing. We get effectively fundamental building blocks that we understand how they work, and then we chain them together and then take account for the interactions. But once we know how this stage works, then we know most of how a differential pair works, which means we know most of how a single stage op amp works. And then it's just what happens if I connect a secondary gain stage to boost my gain, and then what happens if I connect compensation network to do pole splitting, and what effects does that have on the frequency response? So it's taking these basic building blocks and then saying, all right, so what happens if I attach one more thing? What does that do? All right, so let's do this guy down here first. So V out over Vy is RL over RL plus 1 over SC out. Multiplying through by SC out over SC out gives me SC out RL over 1 plus SC out RL. That one's done. Easy peasy. We have something simple. Yay. It stops here. Okay. Next, we're going to do Vy over Vx. So I'm going to get to that page in my notes. You good? All right. So since Vy over Vx depends on ZC and ZE, I'm going to take some time to expand those things out here just real quick so that we know what we're substituting in. So ZC is RC in parallel with, I'll write this out here. RL plus 1 over SC out. So we have those two different branches attached from node Y and the two different paths of ground. So that's what we're taking into account here. So this is going to look like RC times RL plus 1 over SC out divided by RC plus RL plus 1 over SC out. And if I multiply through by SC out, I get RC multiplied by 1 plus SC out RL divided by 1 plus SC out RC plus RL. C looks too much like a parentheses for me. So one thing that's pretty interesting right here, we're going to see this happen a couple of times. I'm jumping the gun here a little bit, but we have a factor of 1 plus SC out in the numerator of a thing that's about to be a fraction, so it's going to be in the numerator of that. We had that same term appear as a pole in the last bit. So we have the same thing as a 0 and a pole, so they literally just cancel each other out, which is why we're going to wind up having 6 different pole frequencies and 6 zeros, but it's going to look like a second order circuit because so many things cancel each other out. Or we wind up having so many poles very close to so many zeros. Okay. So here's ZC. ZE is just RE in parallel with 1 over SCE. So I'm going to make this look like RE over SCE divided by RE plus 1 over SCE, which is simply RE over 1 plus SCE RE. Everybody okay with that? All right, so now we're just going to substitute these things in to our transfer function between Vy and Vx. So Vy over Vx is equal to negative GM ZC over 1 plus GM ZE, which looks like negative GM RC multiplied by 1 plus SC out RL over 1 plus SC out RC plus RL, all of this divided by 1 plus GM RE over 1 plus SCE RE. Are we okay with this? Anything seem wild or wacky? So what I'm about to do here is I'm going to multiply this fraction by 1 plus SCERE over 1 plus SCERE to get rid of my denominator of my denominator. Okay. What that is going to give us is negative GMRC times 1 plus SC out RL times 1 plus SCE RE over 1 plus SC out RC plus RL divided by my stylus roll right here, GMRE plus 1 plus SCE RE. And what I'm going to do now is I'm just going to effectively express the denominator in a slightly different form. Okay. So what I'm doing right here, I have a constant plus a term, and I need this to effectively look like two things that are multiplied together in order to be able to get a polar zero out of it. Okay. So I'm going to lump together GMRE plus 1 as my real part. And then I'm going to have an SCERE as my imaginary part. And then I'm going to factor out that 1 plus GMRE. Okay. So I know that I said a lot of words there. What I'm doing here, I'm going to leave my numerator completely alone for now. Negative GMRC 1 plus SC out RL 1 plus SCE RE over 1 plus SC out RC plus RL. And then I'm saying in the denominator, I have one plus GMRE multiplied by 1 plus S CERE over 1 plus GMRE. So work it through in your head here and make sure that algebraically this and this mean the same thing. Anybody have any beef with that? All right. So the last thing that I'm going to do here is I'm just going to take the denominator of my numerator and move it down into the denominators overall, so that I have a factor of negative GMRC over 1 plus GMRE, my midband gain, times 1 plus SC out RL times 1 plus SCE RE divided by 1 plus SC out RC plus RL times 1 plus SCE RE over 1 plus GM RE. So this term, this transfer function gives me 2 poles and 2 zeros, which tends to make sense because it's got 2 capacitors connected to it, and they are not linked together. So we don't wind up getting a polynomial to make our life terrible. Anybody have any questions, comments, concerns about that portion of the algebra? All right, now for the horrifying elephant in the room. Vx over Vtheta, right? So just as a brief aside here, for the CMOS representation of this circuit, when we did it, we effectively called that transfer function 1 and moved along, right? This is me plotting the results of that transfer function. And it starts out at 1 for several frequencies and gradually gets a little bit smaller and effectively settles to something close to 0.75. So it's not quite 1, but over all frequencies of interest here, it is going to look fairly constant. But we're going to go through it anyway, because we're gluttons for punishment. I just wanted to show you guys exactly what it would do. So let's get this popping on an entirely different sheet of paper. All right, so dx over dθ. We defined earlier to be r pi plus 1 plus beta ze over zthev plus r pi plus 1 plus beta ze. And since we've already expanded out what zthev is and we've already expanded out what ze is, we can just directly substitute into this expression. And what I get when I do that is the following thing. I'm going to start with my denominator first because it's much larger than my numerator. And I mean that with respect to how much space it takes on the page. R1 in parallel with R2 times 1 plus SR sig Cn over 1 plus S R sig plus R1 in parallel with R2 Cn plus R pi plus 1 plus beta Re over 1 plus S Re Ce. And then in my numerator, I just have that r pi plus 1 plus beta re over 1 plus s re. Okay. So the next step that I'm going to do here is literally going to take more space than I have on the page, which is why I had to write it landscape orientation and still damn near ran out of room. Okay. So let me just explain what that step is. All I'm doing is giving every single one of these terms in this expression the same common denominator, so that I can cancel all of them out, leaving behind a single fraction, okay? So I'm going to multiply r pi by this times this over this times this. So I'm just multiplying it by a very fancy variation of 1. I'm multiplying this guy by this over this. I'm multiplying this term by this over this. And then I'm doing the exact same thing to r pi in this term in the denominator as I did to the numerator. Okay, so I'm just getting a common denominator for everything so that I can cancel all out and be left with a single fraction. Okay. So trying to think of how to. Do I need to show you how to do that, or did my explanation make sense and we could skip that step so I don't have to figure out how to write that huge thing down? So just to be clear here, all I'm doing is expressing everything with the same denominator. Yes.
I could just take a picture of that and send it for our group chat.
Sure. I'm going to need it back in a moment.
We're not gonna have it remotely on yet.
Good morning.
We won't have to go. Anything with this one. 30 minutes, 40
All right. So skipping that step of multiplying through to get a common denominator, what we are left with is this thing, which I'm going to try very hard to squeeze in here. Okay. So starting with my denominator first, R1 in parallel with R2 times 1 plus S R sig Cn times 1 plus S RE CE plus R pi times 1 plus S R sig plus R1 in parallel with R2 times Cn times 1 plus, excuse me, I got ahead of myself here, S RE CE. And I'm running out of room for denominator, so the rest of the denominator is going to go down here. Actually, let me back this plus sign up just a little bit so that I don't cramp things. 1 plus beta RE times 1 plus S R sig plus R1 in parallel with R2 times Cn. Close that out. So that's my denominator. All of this is denominator. And then my numerator is R pi times 1 plus S R sig plus R1 in parallel with R2 times Cn times 1 plus S RE CE plus one plus beta RE times 1 plus S R sig plus R1 in parallel with R2 times Cn. Okay. So it was at this point, and for whatever reason, not earlier, that I decided that I stopped wanting to do so much hard algebra and make my life slightly easier. Okay. So what I did here is I just lumped together things that kept repeating. Okay. So everything multiplied by this S, I called tau 1. I decided to call it tau because it looks like R times C to me, and that's a time constant. Okay. So then I went through and identified everywhere else I saw tau 1. And so I have it right here. I have it right here. And I had it again right here. So I'm just going to replace every time I see that with tau 1. I'm going to call RE times CE tau 2. And so I see that again here and here. And then I also have R sig times Cn. I'm calling that tau 3. So from here, I have in my denominator R1 in parallel with R2 times 1 plus S tau 3, 1 plus S tau 2 plus R pi times 1 plus S tau 1 times 1 plus S tau 2 plus 1 plus beta RE times 1 plus S tau 1. So that's my denominator. And then my numerator looks like R pi times 1 plus S tau 1, 1 plus S tau 2, plus 1 plus beta RE, 1 plus S tau 1. What I then did was expanded all this crap out so that I could see, like it should be fairly obvious here. I have a 1 plus S times something plus a 1 plus S times something. I'm going to wind up with an S squared bit. All right, an S squared bit, and then an S bit, and then a constant term. And then I have a number multiplied by 1 plus S, so that's going to add to my S and add to my constant term. So effectively, I have a second degree polynomial in my numerator. If I expand all this stuff out, I also have a second degree polynomial in my denominator. So I just solve for the coefficients of those polynomials. So what I found was for my numerator, AN, so the coefficient of my, actually, let me give you one more step here, so this will make more sense. So I have AN times S squared plus BN times S plus CN over AD times S squared plus BD times S plus CD, where if you're wondering, N is for numerator and D is for denominator, so I didn't get things mixed up. From here, I determined that AN was R pi times tau 1 times tau 2. BN was R pi times tau 1 plus tau 2 plus 1 plus beta RE tau 1. And CN was R pi plus 1 plus beta RE. The coefficients on my denominator, AD, were given by R1 in parallel with R2 times tau 2 times tau 3 plus what I had in my numerator AN. BD was R1 in parallel with R2 times tau 2 plus tau 3 plus BN. And finally, CD was R1 in parallel with R2 plus CN. And from here, I was able to use the quadratic function negative b plus or minus the square root of b squared minus 4ac in order to calculate my poles using these three, or excuse me, my zeros using these three values, and my poles associated with that transfer function using these three values. And I believe at this point I have everything done, because we should wind up having 6 poles and 6 zeros. So that's how I solved it. Yes. So for this circuit, it's a little bit hard to tell. Let me scroll way back up to the beginning, right? So we have 3 capacitors, so the short answer is at least 3, okay? Where we get more is where things effectively interact with each other, right? So for this Vx, or excuse me, for this Vthev over Vn, right? There's only one capacitor tied to where we're doing that. So we only get 1 pole and 1 zero. For Vx over Vthev, we have the capacitor over here and this capacitor over here. So we get 2 from that. From Vy over Vx, we have this capacitance and this capacitance. So we get 2 from that. And then from V out over Vy, we only have this single capacitance. So we got 1 from there.
So how do we have 6 poles and zeros if we have a quadratic? That'd be 2.
So
One
one pole, excuse me, 1 0, 1 pole.
Oh,
All of
that was
it's-
just Vx over Vthev.
Yeah, so we only get 2 from Vx over Vthev,
Yeah.
but we've developed 4 more from all of our other relationships because we would then multiply this horrifying thing together. which would actually turn out to be in the right form because I took the time to express this part in terms of the midband gain multiplied by a frequency dependent transfer function. And then everything else was just simply in a ratio of pole, 0 over pole. But since I'm only asking you to identify poles and zeros, and also because you don't have a legal sheet of paper to turn landscape in order to multiply all that crap through by, just look at each transfer function and get the poles and zeros associated with that.
For that gain that's right there, it's from 335, right? But when I found it in my notes, it's instead of GM, it's GM plus 1 over pi or pi. So yeah, do we just ignore the R pi?
Let's call it yes, because I honestly don't know what you're referring to. So I'm just gonna leave it like this because I've put too much damn thought into this. So that's problem 3A. 3B is much more straightforward because I specifically tell you to use the Miller method to split your thing. So inherently what I mean, if we looked at 3B, let me redraw this real quick and then we'll just talk about it briefly because we're almost out of time after solving half a problem. Yeah. So here's R1. Here's R2. Here's, VN. R sig. It's a BJT, not that. So remember at high frequencies that all those capacitors that we had in our low frequency circuit should look like short circuits. So that's why we no longer have any emitter degeneration here. So here is RC. Here is RL. Here's V out. And I specifically told you that SB, I think, can be neglected, or whatever the equivalent of that is for a BJT. I can't even remember off the top of my head. But effectively, you're only going to have to take into account this capacitor, C mu, and this capacitor, C pi, right? C pi is just in parallel with R1 and R2, so that's fairly straightforward. C mu links the base node to the collector node, and so I tell you very explicitly to use the Miller method to split a portion of it, put it in parallel with C pi, and the other portion of it would be in parallel with RC, RL. And at that point, it's exactly what we did in the notes for the Miller method. The only difference is that RL is now in parallel with RC. Other than that, it is 100% from the notes.
What do you mean by split it up?
Did you not pay attention at all when we talked about the Miller method?
It's behind now.
So what the Miller method allows us to do is if we have a floating impedance between two nodes that we know what their DC transfer function should be, we can apply a portion of that capacitance or a portion of that impedance to the input node of that transfer function and a portion of that impedance to the output node. Go to the notes or go watch the video for high frequency response of common source amplifiers. And it will be literally the exact same thing that we did except that RL and RC are in parallel. I mean, you will have to take into the account that we're going to have a resistance R pi as well, but R pi appears between the base node and the emitter node. So that's just going to be in parallel with this other stuff as well. So B is 30 times more simple than A. B took wherever it is. I redrew the circuit 3 times and then all my analysis is right here. This is way, way, way more easy. All right, so homework set number 5 I posted yesterday. It already has the numerical solutions. I did notice an error in what I posted last night, so I re-uploaded it today with corrected solutions for one of the problems. In my MathCAD sheet, I had RL as 1 kilo ohm instead of 20 kilo ohms. Homework set number 5 is only MOSFETs, so no extra thinking or anything like that. And it's effectively almost exactly what we did in class, except that I included an output stage having a capacitor in series with a resistor. For problems 1 and 2, I very explicitly ask you to use the method that associates a node with, or a pole with each node effectively. So if we, let me pull it open real quick. So effectively, the capacitance associated with node X is just the 85 nanofarad capacitor. The resistance associated with node X. So we have 200 ohms of resistance in parallel with 1 over GM, which I give you what GM is. And then that's going to be in series with the 500 ohm resistor when we ground this node out. So that's RX and CX. For RY, we see 200 in series with 20K in series with 3K. CY is 25 nanofarads. Calculations done. Right. So effectively, all I'm saying here, this capacitor sees 20 in series with 3 because these two ground nodes are tied together. 85 sees 500 in series with 200 in parallel with 1 over GM, because this ground node is tied to this ground node, which is tied to the ground node that we see looking up as well. So that's how you would do problem 1 and problem 2. Just problem 2 uses the parasitic capacitances. Problem 3, you can do the same thing, or you can do the direct analysis. Literally either way, you will wind up getting the exact same numerical answers. I mathematically proved it to myself yesterday evening, waiting to get hit in the face. So, problems like these are much more likely to show up on your exam than the torture I put you through in homework set number 4. I would, so that's actually something that I wanted to ask you guys about. Are you sure you want to have numerical answers on this test?
Oh, no, we want numerical answers from homework so we can check.
Okay.
We don't want it for the test.
I honestly would rather not have numerical answers on the test, because to me, that's a waste of time, because it's just plugging shit in. And then you have opportunities to make mistakes typing stuff in your calculator because you don't have a lot of time to think through things. So I would prefer that your exam is effectively being able to identify things and then regurgitate shit back at me from your notes. That's my hope. I want this upcoming exam to be open notes. And so what I mean by that is you might want to bring your 335 notes to, just in case there's something that you don't remember. Okay. So like literally just bring all the notes you've had for the last 5 months. I'm going to give you 3 circuits. One's a common source amplifier, one's a common gate amplifier, one's a common drain amplifier, and I'm going to ask you to find some poles Full stop. That's going to be your exam. If you have followed what I've been doing, sorry, Luke, picking on a different Luke today. If you have followed what I am doing, this exam should be pretty straightforward because it should be, oh, I just need to find this part of the notes and then do that. So that's my goal for this test. Yeah,
Have the equation jumping when we chop the tree or?
yeah, I'm gonna roam around the room to make sure you're not messaging each other. If you've done your stuff on a tablet, do it on the damn tablet. Yeah. Yeah, you do not need to bring 600 pages of printed out stuff. Don't kill a tree to pass this test. No, I know, yeah, it's huge. Yeah, don't kill a tree for this one. If I had a way to give you all a take-home test that you wouldn't talk to each other about, I would just do that, and then you could do anything, but I know that you're gonna talk to each other, so I'm gonna pretend like you don't know how to send each other text messages and crap while you're in class with me looking at you, so. Really?
So recently, yes, are you gonna post this lecture and what's this lecture before the exam?
Absolutely, yes. I hope to have everything up tonight. My wife has to work late, so I don't have anything better to do tonight than put videos online. So that's my goal, is to catch up on all of the video editing and posting this evening before I go to bed.
For the goals, just certain keys for what- it says frequencies, but I want that.
Yeah, so yeah, everything that I've been doing has been solving for omegas, so let's do that. Yeah, let's leave it. Let's not worry about the dividing by 2 pi parts. Yeah. Let's see what chat says. No numbers. Let's do this like physics. Oh, okay, yeah, that's pretty much it. And then Abdullah says no emphatically to something. I don't remember. I didn't notice earlier. Yeah, okay, so just no, very, very light. Yes,
Also, I'm pretty sure today's the drop date, and they haven't gotten like a grade back on it.
don't drop.
Okay.
Don't drop. Don't drop. Yeah, no, I understand that. I think Logan Bailey said it most succinctly when he said, we're all just riding in this boat and hoping it doesn't sink. Yeah. You need this class to graduate. Don't drop. If you drop this class, you either have to come hang out with me over the summer or you put senior design off by a year. Don't drop. I'm not making any guarantees about anything because I honestly don't have the foggiest clue how anybody's doing in this class. I'm telling you emphatically, though, dropping is a bad idea. I can say that knowing nothing about your grades, because if you drop, you're just, there's no chance of you passing the class and getting into senior design. So does that seem like, I know I put you in a shitty situation. It is much too late for me to do anything about it because we've got 3 hours, so don't drop. Yeah. It is what it is.
People make like a 5 or like a 10 on, assuming you get 100 on everything else in the class,
Mhm.
you'll have a D.
Yeah.
So,
Just that is another very true thing. You literally just need a D to get out of this horrible class that I'm inflicting upon you. Yes.
So what exam?
Well, I thought exam 1 was pretty easy. You guys told me I was very wrong. Still haven't graded it yet. You emphatically told me that I was not correct in thinking that it was easy. It is my intention to make this exam very straightforward. Bring your notes, you shall pass. I haven't made it yet, so I can't say anything beyond that, but it is my intention to not torture you all with this.
Does that mean that exam 3 is gonna be the hardest?
I'm saying on the first two.
So yeah, exam 3 is going to be all about feedback amplifier circuits. The hardest part of that is figuring out, so effectively there are 4 parts of any feedback system. You have like your input, your sense mechanism, your feed forward system, and then your feedback mechanism, and figuring out what parts of the circuit those things do, or those are, is the hardest part. After that, it's just one equation over and over and over again. A times K over 1 plus A times K. You just got to figure out what part is K, which represents the feedback network. You got to figure out what part is A, which represents the gain. And then as long as it's negative feedback, which everything I'm going to give you is negative feedback, it's going to be that. Yes. Anything else
How hard is number 4?
on this homework set? I haven't worked it yet, but the intention there was not for it to be difficult. You're using the, let's see, open circuit time, short circuit time constant method for the first part and open circuit time constant method for the second part. So that means you literally just leave one capacitor acting as a capacitor, turn all of the others either into short circuits or open circuits and see what resistance is connected, and then calculate that as an approximation. Yeah, that's like circuits 1 level crap for the most part. So 3 was supposed to be challenging. I might have asked you guys to bite off a little bit more than you, definitely I asked you to do more than you were comfortable with. But I think the methodology, in my opinion, as a jackass with a PhD, is fairly straightforward. It's just seeing what we've seen before and applying those same relationships, but now we have to deal with impedances as opposed to just purely resistances. Again, I know that I'm a jackass with a PhD who has done this stuff for more time than you, but that's what you were supposed to get out of that problem. The algebra definitely bogs things down. Not going to lie and say that it doesn't, but you all are about to be seniors and you've been doing algebra since you were 10. So just saying. Did you say obviously not long enough?